with the Unix you can increase your priority but not increase the priority. Nice, this utility of nice is used for decreasing your priority. Okay. The example that I showed you is run on Windows, so the priority numbers are kind of in reverse. In Unix, the number, if the number is higher, then your priority is higher, not lower. Let's continue with the interactive system process scheduling. Another idea is to use the shortest process next. Actually, we did the same thing with the batch scheduling algorithms. We said that if you run the shortest process first, that will increase your throughput. Why don't we use the same idea? The problem is that for the interactive systems, we don't know how long they are going to take, how long they will take to run. It changes from time to time. How long it will take to block for a process when they are using the CPU. It is not as simple as using them as batch jobs, because in the batch jobs, since there is no interaction, it will take almost the same time, and the times are like maybe in terms of hours or days. So they are very, very long times, and I know how long it would take the last time I run that algorithm or program or the process. If I wanted to do the same thing with the interactive systems, maybe we can get an estimate. Okay, it is hard, but instead we can use historical data. We can use historical data to make an estimation of how long it's going to take to complete this run of the interactive process. For this, let's say the first time my interactive process used T0 time of T0, maybe let's say 10 milliseconds, okay? And for the second time, it used 20 milliseconds. So I would expect that, okay, something like this maybe. Alpha times 10 milliseconds plus 1 minus alpha times 20 milliseconds is my expectation now. If I set my alpha to be 0.5, that means that in this case it will be 5 plus 10, right? So it will be 15 milliseconds. I am expecting that my process will run 15 milliseconds. Okay? So this is my expectation, and I can use this expected time to run a scheduling algorithm that lets the shortest process run next. Okay? So these are the formulas. To calculate this T2 time from T0 to T1, multiply T0 with alpha, and multiply T1 with 1 minus alpha, and that will give me T2. And I will do the same thing again. If I for the T3, what I would do is multiply this one with alpha again, multiply this with alpha, and this one with alpha again, plus T2 times alpha, and this will give me T3, and this is what I have. Okay, so continue doing this. Next time I would calculate my expected CPU usage time, but it looks like it is getting more and more complicated, and since scheduler is a very critical task to run, it should not take that much CPU time. If I keep multiplying and adding these numbers, my scheduling algorithm will take lots of time to run. So that's not a good thing. So what should I do? The solution is take alpha 0.5. Okay, take alpha 0.5. In that case, if I do that 0.5, my calculations would be a lot easier. Let me go there and show you the real. Okay, so if I take my alpha as this 0.5 or 1 over 2, what I am seeing here is this T0 is the T0 time. This is T2, Okay, this is how I calculate T2, and this is how I calculate T3, and this is how I calculate T4. So I always keep dividing T0 with a larger number, okay, with a larger number. So I am taking the weighted average with this formula. If I take this alpha as 1 over 2, it is easy to implement. All that is needed is to add the new value to the current estimate and divide the sum by 2. That means that I need to do this. I need to do, okay, this. When I calculate Tn, I should do Tn minus 1 plus Tn minus 2 over 2. Okay, so that's the formula. By adding two numbers and dividing by them 2, okay, I would get this Tn number. And I keep calculating this Tn, and this will be my shortest I expected time duration. Okay, this is my expected time duration for my process. And I can run exactly the same algorithm as the batch processing one. I think it was around 100. Okay, this is, remember in the batch processing scheduling algorithms, okay, we said we have 3 of them. Okay, the second one was the shortest first. So the shortest first was, I don't know what happened to this picture, but shortest first was choosing the shortest job first, then the second one, then the third one. This is how it was was working. So run the shortest next, but to get a better estimate, I use this aging estimation of the expected interactive process running time. This is the formula. If I use alpha as 0.5. Okay, any questions?
Hocam, alfa 0 ile 1 arasında olmak zorunda değil mi?
Yes, it has to be between 0. It has to be between 0 and 1. Otherwise, this formula wouldn't work. Otherwise, I mean, let's say if my T0 is 10 and this one is 10 too. Okay. So what I would expect as T2 as 10. I should not change because it did not change. So if you make alpha more than 1, that would make your estimation larger than 10. Okay, so it has to be between 0 and 1. So what is the idea? If my process keeps running in 10 milliseconds, so my estimation should be 10 milliseconds. Okay? So if you don't use alpha between 0 and 1, your let's say it is 2, in that case your results will change. So this is a weighted average. How much weight should I give to the last observation, and how much weight should I give to the previous observation? Since it's a weight, those weights should add up to 1. Okay. Any questions? So this is the shortest process next. Another interactive scheduling algorithm is guaranteed scheduling. Okay. Let's say I have n users or processors on a system. So I give 1 over n of CPU time to each process or to each CPU. Okay. That means that when I run n processes, I expect that each process or each user should get the 1 over n of the CPU. At the end of my first round, I calculate the CPU time for each process. If the CPU time is different for some processors or for some users, then I adjust their priorities or their quantum times so that they would use less CPU time or more CPU time. This is called guaranteed scheduling. Okay, look at the ratio of the two. Okay, 0.5 means that, okay, 0.5 means that it had only used half the CPU time. Let's say, okay, I have 10 processes. Okay, for a second, each process should use 100 milliseconds of CPU time. Okay, So at the end of the first second, I looked at the CPU usage time. Process number 1 used 50 milliseconds. Process number 2 used, let's say, 100 milliseconds. Process number 3 used 100 milliseconds. It goes that way, okay? So I know that each process should use 100 milliseconds. So this means that this one used half the time that it needs to use, okay? This one used 2 times the time that it needed to use. So this one used too much, this one used too little. This one used just about the expected time. So this one will get higher priority, this one will get lower priority, this one will get the same priority. Okay. So I just look at the ratio of use time versus use time over the expected time. Expected time and expected time. And 0.5 will get, okay, this is 0.5, will get higher priority. This is 2 will get lower priority. This will get the same priority. This is called guaranteed scheduling. So it is trying to be fair between the users or between the processes. It measures how much they use the CPU. It is not that difficult to understand how much CPU they are using. Okay. Any questions? Another one, lottery scheduling. Since these interactive systems are so popular and it is used by many different systems. It was used by the web servers. It was used by the personal computers or the cell phone operating systems. There are many scheduling algorithms for this kind of operating systems. Another one is lottery scheduling. You give lottery tickets, piyango bileti gibi yani. You give lottery tickets to each process, okay? And when you are doing the scheduling decision, you just pick a random ticket, okay? Whoever holds the ticket gets the CPU. It's like lottery scheduling, actually, like lottery picking, okay? So you give lottery tickets to each process, and when you are doing the scheduling, you just pick a random ticket, and you say that whoever is holding that ticket will get the CPU. If you want some of your processes, to use more CPU time, you give them more tickets. Instead of giving one ticket, you give more ticket. In that case, that process will have better chance of using the CPU. Okay? In that case, it will have better chances of getting the CPU. The advantage of this approach is the tickets can be exchanged between the process. If I am blocked and if I'm waiting for a lock, maybe I can maybe I can donate my tickets to other process that is holding the lock. It has these kind of advantages. Piyango bileti veriyor musunuz gibi yani adama piyango çekilişi yapıyor her seferinde scheduling decision'ı verileceği zaman. Kim çalışacak şimdi karar verecek. Adam bir tane piyango bileti seçiyor. Bu biletin sahibi kim? Oradan bize diyor ki öyleyse sen kullanacaksın. Eğer higher priority bir prosesiniz varsa ona daha fazla piyango bileti veriyorsunuz. Random çekiliyor yani. Kim çalışacak? Eğer böyle olunca hiç kimse açlıktan ölmüyor çünkü elindeki bilet sayısı çok az olan birisinin bile CPU kullanma ihtimali var, çıkabilir. Ama daha çok kime çıkıyor piyango? Piyango daha çok kime çıkıyor?
Hayır.
İstanbul'a çıkıyor değil mi?
Evet.
Nimet ablaya çıkıyor. Öldü mü Nimet abla? Niye? Çünkü Nimet abla en çok şey satıyor, bileti satıyor. Onun gibi. Ama hala işte Rize'nin en ücra köyünün en kıyısındaki adama çıkma ihtimali var. Onun da bileti var çünkü. Eğer birileri biletlerini başkalarına vermek istiyorsa verebilir. Hangi durumda verebilir? İşte priority donation vardı ya, onu burada rahatlıkla yapabilirsiniz. Tamam. Tesadüfilik var ama bu işlem saniyede ya da dakika içerisinde binlerce milyonlarca defa daha olduğu için aldığınız zaman ortalamada yani tüm piyango işine bakarsanız ortalamada baktığınız zaman en çok bileti alana en fazla şey çıkmıştır. İkramiye çıkmıştır. Evet.
Hocam mesela bir tane proses işini bitirdiğinde, ranlanması bittiğinde elindeki kalan piyango biletlerini diğer prosesler...
Piyango biletini dağıtmak scheduler işi.
schedule'ı mı?
Evet. Ben yani işim bitti, ben bunu arkadaşıma veriyorum falan olmuyor.
Yani 10 tane piyango bileti varsa ve işi bittiyse o 10 bilet yanıyor mu?
Gecenin şeyi döndü.
Yani ranlanması bittikten sonra o 10 bileti diğer prosesörde
Scheduler
harcamıyor.
ortada kaç tane bilet olduğunu biliyor, tamam mı? Yani 10 tanesi yanmış, onun için önemli değil.
Geri schedule'ı geri alıyor 10 tane bir daha.
Etrafta 110 tane bilet vardı, 10 tanesini tutan birisi öldü. Demek ki şimdi 100 tane bilet var, değil mi? Biliyor yani. Bir biletin manasının ne olduğunu biliyor. Bir bilet demek, 100 tane bilet varsa bir bilet demek CPU'nun %1'i demek. Onu biliyor. Eğer sen bir kişiye CPU'nun %1'ini kullanmasını istiyorsan bir bilet verirsin. Ama ortalıkta 110 bilet varsa bir bilet vermek CPU'nun 110'da biri demek. O zaman belki ona işte 2 bilet vermen gerekiyor. Biletin yanmasının önemi yok. Önemli olan toplam bilet sayısı, oran. So this is called lottery schedule. It is based on randomness, but if you take the average, you know who is the winner, right? Yani piyango işinde kim kazanır? Bileti satan kazanır. Kesinlikle kazandı. Bellidir. Piyango işinden piyango biletini satın alıp da bir şey kazanan olduğunu görmemiştir. Okay. Another one is fair share scheduling. These are all related. Okay. In some systems, process don't complete, but users do. Okay. If I am the user and if I have 5 processes running, and there is another user, he has only user A has 1, 2, 3, 4 processes. Okay. User B has only one process number 5. So if I try to keep the balance between these processes, user A will get 80% of the CPU time, right? So this is not fair between user A and user B. It is fair between these processes, but it is not fair between user and user B. So we don't want to encourage forking just to get larger share of the CPU. The user A is kind of knows his things. He artificially creates these processes, okay, 4 of them. He knows that he's going to get more CPU time by creating more processes. So in order to prevent these kind of problems, make decisions based on the user CPU consumption instead of process CPU consumption. Maybe run this algorithm guarantee scheduling by measuring how much the user uses the CPU instead of how much the process uses the CPU. Okay, so make your decision based on the user, not based on the processes. Again, priorities can still apply. If the processes of user A is too much, then I can lower the priorities of these, but keep the priority of this one higher because this one has only one process. Okay, so this is called fair share scheduling. Questions? These are very simple algorithms, and each of them has different point of view, and usually you combine ideas from different schedulers to make a I don't know why this is empty. Maybe I can go there. Lottery scheduling, okay, fair share, okay. Okay, so if I go back to, again, remember what we did first? We said we are going to look at the batch system schedulers, first come, first served, shortest time remaining. These were the batch schedulers. And then we looked at the interactive schedulers. In the interactive schedulers, the main thing was the time sharing, the main thing was the switching, preemption, and quantum time, right? It was based on all quanta and the priorities. 2 things, quantum time and the priorities are the things for the interactive systems. Now we are going to look at the real-time systems. Okay? In the real-time systems, the thing is meet the deadlines. Remember what we said at the beginning? We said that in the real-time systems, the main purpose is meeting the deadlines. If you don't meet the deadlines, then most of the time you are in trouble. There are two types of real-time systems. One is the hard real-time system, the other one is the soft real-time. In the hard real-time, if you don't meet the deadline, then you are dead. Okay, you are as good as dead. Your system doesn't work if you don't meet the deadline. What kind of real-time systems are these? For example, these are a nuclear power station control software. It has to be real-time. If you don't meet the real-time deadline, then your plant will explode, or your car brake will not work, or bad things will happen. So these are hard real-time systems. There are soft real-time systems. These systems try to meet the deadline most of the time, maybe 99% of the time. If you miss the deadline, it's not a good thing, but it is not end of the world, okay? It is nevertheless tolerable. It is tolerable, but it is not end of the world. For example, a DVD player, okay? DVD player is supposed to show 20 frames per second, okay? If you show 25 frames per second for 2 hours, it is okay. But if you just miss one frame in an hour, maybe the viewer, maybe the user will notice it, but it will not be end of the world because it is tolerable. It is tolerable. Sometimes that kind of problem happens. If you miss 2 frames per second, instead of showing 25 frames, you sometimes show 23, sometimes you show 21. For most of the time, that's not tolerable because you are missing your deadline most of the time. So for soft real-time systems, it is okay to miss your deadline once in a while, maybe 1% of the time, maybe one out of 1,000 times. But for the hard real-time systems, there should never be a deadline missing. Okay? So these are two types of real-time systems. When we come to real-time systems, the important thing is this. Okay, if I have, let's say, M processes, there are M processes. Okay, the process number I, okay, I have M processes. The process number I uses this much CPU time, Ci. Okay, let's say it uses 100 milliseconds of CPU time, and this process number I runs every pi milliseconds or seconds. Okay, let's say this process number M uses 100 milliseconds. Okay, when it runs, but it runs every 3 seconds. So that means that it uses 100 milliseconds, but it runs every 3,000 milliseconds. That means that it is using 1 over 30th of the CPU time, right? So it is using 1 over, if I remove these, so it is using 1 over 30th of the CPU time. If I have 30 more processes, if I have 29 more processes like this, my CPU can take this load. But if I have 100 of this one, if I have 100 processes like these, and each one is trying to use 1/30th of the CPU time, I cannot keep this load in this real-time system. I cannot meet the deadlines of all these processes because I don't have enough CPU time for all of those. So this is the formula. If my processes are schedulable on my system. There are M processes. For each process takes Ci amount of CPU time, and each process takes Pi. Each process takes every Pi seconds. Okay, this system is valid, can be run, okay, can be kept up if this summation holds. If this summation is less than 1.0, then that means that I can schedule all of these tasks in my real-time system. Otherwise, some of the jobs has to wait for some duration. If they have to wait, then I will miss my hard real-time tasks, or sometimes I will miss my soft real-time tasks. We didn't have a calculation like this for our interactive systems. Because in the interactive systems, I didn't have any constraint on meeting the deadlines. Okay, meeting the deadlines. Okay. Any questions on those? And remember, there is always a switch overhead. There is always a switch overhead. Okay. Maybe I should do this 1.0 minus switch overhead. Okay, because switching between M processes will take some time too. Okay, so this is a better formula. And let's say switch overhead takes 10% of the CPU time, so this should be less than 0.9 then. Okay, so this is a very common formula used by the real-time systems. Real-time systems. If you are running a single process, this calculation is very simple. Okay, if you are not using the CPU 100% of the time, then you are okay with a single process. If you have more than one process, then you need to make this calculation. Okay. Any questions? Okay. So this is something that we need to keep in mind. And there is an example. I have a soft real-time system with 3 periodic events. Okay. Each one will take these periods. One will run every 100 milliseconds, the other one will run every 200 milliseconds, and the other one will run every 500 milliseconds. So P1 is 100, P2 is 200, and P3 is 500. And then these events will require 50 milliseconds, 30 milliseconds, and 100 milliseconds. C1 is 50, C2 is 30, and C3 is 100. So if I divide this number by this one, and this one by this one, so what I do is 50 over 100 plus 30 over 200 plus 100 over 500. This should be less than 1.0. Okay, is it? Yes, it is. So this is 7 and 85. 0.85 is less than 1.0. So this is schedulable. Okay, schedulable. That's the calculation. That's the formula. Okay, it's a very simple formula. Very simple calculation. Without this calculation, you cannot know if your process is schedulable on a real-time system. Okay. Any questions? Okay, so the thing is that my processes are very regular behaving processes. They say that I will run 2 times in a second, this one says. This one says I will run 5 times in a second. This one says I will run 10 times a second. These are very regularly running processes. The problem is if I have a priority events, you don't know when that process is going to run. Sometimes it runs 5 times a second. Sometimes it runs once only an hour. So these are a priority events. So that formula is not valid for these kind of processes. So working on this kind of systems is harder, and we will not talk about those. Okay.
What about context switching? If our equation is equals to 1?
Yeah, but that's what I said. We should be careful about switching overhead. That's why I said 1.0 minus switching overhead. Okay. So I ignored this formula. Ignores the switching overhead, but it should be there. Maybe I can say that one of these processes are switching process. Okay. Maybe it is taking the time for the switch. But yes, that's a valid point. You should be careful about switching overhead. Okay, let's talk about, I had a few questions about how about thread scheduling. Let's talk about thread scheduling versus, now I When I talk about scheduling, we always talked about process scheduling, but thread scheduling is something important too. And it depends how you. It depends if you implement your threads in the kernel or in the user space. Okay, if you implement your threads in the user space, then the kernel doesn't know about your processes, right? Kernel doesn't know about your threads. Okay, so the kernel thinks that there are two processes only. If I want it to be shared, okay, if I want it to be fair, then this will get this one and this one will get equal priorities, the same priorities. If I am running round robin, okay, all the kernel sees that this is process A and process B, then it goes back to process A. So they will have equal quanta, process A and process B. But within process A, there are 3 threads, and within process B, there are 4 threads. Okay, there are 4 threads. If the operating system says that it is time for process A to use the CPU, the process A will schedule its own threads in its own quantum time. Okay, so it will say that A1 will run, A2 will run, and A3 will run, then A1, then A2, then A3. It will go this way. Okay. With this kind of scheduling mechanisms, when you implement your threads in the user space, you cannot do this. A1, B1, so this is B1, this is A1, okay? A1, B1, then A2, B2, A3, B. So you cannot switch between from this thread to this thread, because switching is done by the operating system between these two processes, okay? So this is something to do with the decision of implementing your threads in the kernel space or the user space. Okay. Process A and process B are run preemptively. They have their own quantum time, but these threads they don't have their quantum time because the scheduler here the scheduler inside my process A is not a preemptive scheduler. It cannot be. Why? You cannot run your threads, if you implement your threads in the user space, you cannot run your threads preemptively. You cannot stop a thread from running and let the other thread run. Why?
Cooperative.
Why?
Cooperative.
But that's the idea of threads versus the processes, but it is not possible. But I mean, if you wanted to do that, you cannot do it. You cannot stop a thread from running and let the other thread run if you implement your threads in the user space.
Çünkü user'da olduğumuz için işletim sistemi zaten bilmiyor threadlerden habersiz. Eğer kernel'da olsaydı, kernel space'de olsaydı belki olur.
How do you do the preemption? How do you do the preemption in the kernel space? By doing what?
When one thread is going to block, it asks the operating system if it's going to block, and it changes to...
That's how you switch between the threads, yes. I mean, if this one blocks, then the scheduler will say that this one will run, and this one blocks, the scheduler says that this one will run. But I'm saying that the thread number one is CPU bound. It will not block, and it will keep using the CPU. How do you stop this thread from running inside this process? You cannot. It has to run. What?
Hocam şey diyecektim, kesintili kılıp interruptlarıyla değil mi?
If you use the interrupts, okay, if you use the interrupts are handled by the operating system, not by the processes. User processes, they don't have access to the interrupts. You cannot control your interrupts. If you have a timer interrupt, your whole process will be stopped and control will go to the kernel space. And the kernel space will switch from this process to this process. Okay? So you cannot do preemption. You cannot do preemption within your threads if you are doing the user level threads. So how do we solve this problem? We don't solve this problem. So how come I can use more than one thread inside a process? we know that the threads are cooperating because they are written by the same program, okay? So this one knows that if I keep using the CPU, these two will start with that. That means that my process will not be successful. So this one calls what? This one calls sometimes, once in a while, thread yield, right? This one calls thread yield. When this thread yield call is made, the scheduler will get this call and it will switch from this thread to this thread and this thread. But you cannot make the switch from this thread to this thread. Only you can do between these three inside the same quantum. Inside the same quantum. If the time is up for this process A, then I will go to process B, and process B will start doing the same thing. Okay, process B will start doing the same thing. But if I implement my threads within the kernel, then it is possible to have these kind of scheduling decisions. A1, then A2, B1, then A2, then A1, B1, A2, B2, it goes that way. Because the scheduling decisions are done by the kernel, and kernel has all the control of the interrupts and everything. Okay, so the scheduling of the kernel level threads are more flexible, but we know the problems with the kernel level threads. They are more expensive because you need to make system calls, and once you switch. When you switch between this thread to this thread, it is a full context switch. It is not that cheap anymore. Switching from A1 to A2 is cheaper. Why? Because I am using the same address space. I don't have to invalidate my cache and my page tables and etc. So switching threads within the same process is much cheaper than switching from this thread to this thread. I know that too. So there are advantages and disadvantages. I know all of these together. Okay, so let's look at this slide and we will stop afterwards. Since the kernel knows that switching from a thread in process A to a thread in process B is more expensive, maybe if my scheduler is smart enough, maybe my scheduler, even though it can do A1, B1, A2, B2, since it is smart, it will say that this is expensive, maybe I should do this A1, A2, A3, and as long as it goes, it will do that. If it has to switch from this thread, then do this thread. If it has to do it, then it will do it. But if it is okay to keep running these, it will keep running these, because it knows that switching from this one to this one is less expensive, cheaper. So if I have a smart kernel scheduler, thread scheduler, I can implement such a scheduling algorithm. Okay. Again, user level threads can employ an application specific thread scheduler. Okay. For example, for the web server, remember the web servers? How many threads did we have? We have the worker threads, and we have a scheduler, right? So in this case, if I have a dispatcher thread, which is the most important thread, maybe that thread should get the more time. So in the user level threads, I can do this kind of adjustment. I know that one of the threads is more important, so give more priority to that thread. Always run that one first, then let the others run. The kernel wouldn't know this kind of differences. If I implement my threads in the kernel wouldn't know that. The kernel wouldn't know that this one should be run always first. These are just worker threads. So these are the advantages of user level threads actually. Okay, so again, we will not say that user level threads are better than the kernel levels or kernel levels are better than the user level. There are advantages and disadvantages. That's why most of the thread libraries are done in a hybrid way, right? They are both. They have parts in the user space and they have parts in the kernel space. We don't have any pure kernel implementation of the threads, or we don't have any pure user level threads in practical applications. Okay, so that's it for today. Tomorrow morning we will continue, we will finish up with this chapter and we will start the memory chapter.